numbers for complex numbers cmath module. This module provides access to mathematical functions for complex numbers. The functions in this module accept integers, floating point numbers, or complex numbers as arguments. They will also accept any Python object that has either a complex or float method. These methods are used to convert the object to a complex or floating point number respectively, and the function is then applied to the result of the conversion. For functions involving branch cuts, we have the problem of deciding how to define those functions on the cut itself. Following Kahan's branch cuts for complex elementary functions paper, as well as NXG of C99 and later C standards. We use the sign of 0 to distinguish one side of the branch cut from the other. For a branch cut along a portion of the real axis, we look at the sign of the imaginary part, while for a branch cut along the imaginary axis, we look at the sign of the real part. For example, the cmath dot square root function has a branch cut along the negative real axis. An argument of complex minus 2.0 minus 0.0 is treated as though it lies below the branch cut, and so gives a result on the negative imaginary axis. cmath.sqrt complex minus 2.0 minus 0.0 minus 1.4142135623733095J. But an argument of complex minus 2.0 0.0 is treated as though it lies above the branch cut. cmath.sqrt complex minus 2.0 0.0 1.4142135623733095J. Conversions to and from polar coordinates. A Python complex number z is stored internally using rectangular or Cartesian coordinates. It is completely determined by its real part z dot real and its imaginary part z dot image. In other words, z is equal to z dot real plus z dot imaginary into 1j. Polar coordinates give an alternative way to represent a complex number. In polar coordinates, a complex number z is defined by the modulus r and the phase angle phi. The modulus r is the distance from z to the origin, while the phase phi is the counterclockwise angle measured in radians from positive x-axis to the line segment that joins the origin to z. The following functions can be used to convert from the native rectangular coordinates to polar coordinates and back. cmath.phase x return the phase of x, also known as the argument of x, as a float. Phase x is equivalent to math.a10 x.imaginary x.real. The result lies in the range minus pi to pi, and the branch cut for this operation lies along the negative real axis. The sign of the result is the same as the sign of the x.image even when x.image is 0. Phase complex minus 1.0 0.0 3.141592653589793. Phase complex minus 1.0 minus 0.0 minus 3.141592653589793. Note: the modulus absolute value of a complex number x can be computed using the built-in ABS function. There is no separate cmath module function for this operation. cmath.polarx return the representation of x in polar coordinates, returns a pair r, phi, where r is the modulus of x and phi is the phase of x. Polar x is equivalent to ABS x, phase x. cmath.rect r phi return the complex number x with polar coordinates r and phi equivalent to r multiplied by math.cos phi plus math.sin phi into 1j. Power and logarithmic functions. cmath.x expx return e raised to the power x, where e is the base of natural algorithms. cmath.log x base returns the logarithm of x to the given base. If the base is not specified, return the natural logarithm of x. There is one branch cut from 0 along the negative real axis to minus infinity. cmath.log 10 x return the base 10 logarithm of x. This has the same branch cut as log. cmath.sqrt square root x return the square root of x. This has the same branch cut as log. Trigonometric functions. cmath.a cos x return the arc cosine of x. There are two branch cuts. One extends right from 1 along the real axis to infinity. The other extends left from minus 1 along the real axis to minus infinity. cmath.a sin x return the arc sine of x. This has the same branch cuts as a cos. cmath.a10x return the arc tangent of x. There are two branch cuts. One extends from 1j along the imaginary axis to infinity j. The other extends from minus 1j along the imaginary axis to minus infinite j. cmath.cos x return the cosine of x. cmath.sin x sin x return the sine of x. cmath.tan x return the tangent of x. Hyperbolic functions. cmath.a cos h x return the inverse hyperbolic cosine of x. There is one branch cut extending left from 1 along the real axis to minus infinity. cmath.a sin h x return the inverse hyperbolic sine of x. There are two branch cuts. One extends from 1j along the imaginary axis to infinite j. The other extends from minus 1j along the imaginary axis to minus infinity j. cmath.a10h x return the inverse hyperbolic tangent of x. There are two branch cuts. One extends from 1 along the real axis to infinity. The other extends from minus 1 along the real axis to minus infinity. cmath.cos h return the hyperbolic cosine of x. cmath.sin h x return the hyperbolic sine of x. cmath.tan h x return the hyperbolic tangent of x. Classification function. cmath.is finite x return true if both the real and imaginary parts of x are finite and false otherwise. cmath.is infinity x return true if either the real or imaginary part of x is an infinity, the false otherwise. cmath.is nan x return true if either the real or the imaginary part of x is nan and false otherwise. cmath.is close a b star real total relative total 1e0 minus 09 absolute total 0.0. Return true if the values a and b are close to each other and false otherwise. Whether or not two values are considered close is determined according to given absolute and relative tolerances. Relative tolerance is the relative tolerance. It is maximum allowed difference between a and b relative to the larger absolute value of a or b. For example, to set a tolerance of 5%, pass real relative tolerance is equal to 0.05. The default tolerance is 1e raised to minus 09, which assures that the two values are the same within the 9 decimal digits. Relative tolerance must be greater than 0. Absolute tolerance is the minimum absolute tolerance useful for comparisons near 0. Absolute tolerance must be at least 0. If no errors occur, the result will be absolute a minus b less than equal to max relative tolerance multiplied by max ab absolute a comma absolute b comma absolute tolerance. The IEEE 754 special values of NaN, INF, infinity, minus infinity will be handled according to IEEE rules. Specifically, NaN is not considered close to any other value, including NaN. INF and minus INF are only considered close to themselves. Constants. cmath.pi, the mathematical constant pi as a float. cmath.e, the mathematical constant e as float. cmath.tau, the mathematical constant tau as a float. cmath.inf float point positive infinity equivalent to float in inf. cmath.infinity j complex number with zero real part and positive infinity imaginary part equivalent to complex zero point zero float inf. cmath.nan a floating point not a number value equivalent to float nan. cmath.nanj complex number with zero real part and nan imaginary part equivalent to complex zero point zero comma float nan. Note that the selection of functions is similar but not identical to that in module math. The reason for having two modules is that some users are not interested in complex numbers and perhaps don't even know what they are. They would rather have math.s square root minus 1 raise an exception that return a complex number. Also note that the functions defined in CMath always return a complex number, even if the answer can be expressed as a real number, in which case the complex number has an imaginary part of 0. A note on branch cuts. They are curves along which the given function fails to be continuous. They are a necessary feature of many complex functions. It is assumed that if you need to compute with complex functions, you will understand about branch cuts. Consult almost any not too elementary book on complex variables for enlightenment. For information of the proper choice of the branch cuts for numerical purposes, a good reference would be the following: Kahan W. Branch cuts for complex elementary functions, or much ado about nothing, nothing sign bit in Israelis A. and Paul M. eds. The State of the Art in Numerical Analysis, Clarendon Press. Thank you.